We've described a recipe. We said it's a sequence of mechanical steps. It's going to capture the sequence of things I want to do in order to compute something. But now I want to get it inside the computer. I don't want to just give it to my friend and have him do all the work for me. So the next question is, how do I capture a recipe inside a mechanical process? Go back to my square root example. I'd like to get a machine that's going to compute square roots for me. Historically, there were two choices here. The first one was to use what was called a fixed program computer. And this would be a computer designed specifically to calculate a particular computation. You've actually seen them. Actually, you may be too young to have seen them, but people my age have seen them. Handheld calculators were a fixed program computer. They did addition, subtraction, multiplication, a simple set of arithmetic operations. That's all they could do. If you wanted it to search the web, good luck. Wasn't going to happen. Very famous historical example was Alan Turing's bomb. This was a machine designed during World War II to break German codes for the Enigma machine, and it was designed specifically for that process. It was also built out of devices you don't see anymore, like vacuum tubes and relays. And you can imagine the challenge of building such a machine, but it was designed to be a fixed program computer. That'd be boring if that's all we could do. I don't want to have to carry around a computer for square root and a computer for cube root and a computer for quadratic root. You get the idea. The alternative is what's called a stored program computer, and that's what you're used to seeing. Difference with the stored program computer is that you can load into it that description, that sequence of instructions, that recipe. And then inside that computer, there's going to be a set of parts that are going to do those instructions when I ask them to. And in particular, there's going to be a special program inside the computer, typically called an interpreter, which when you start it up is going to walk through each of those sequence of instructions in turn, doing the computation I want. And the advantage of a stored program computer is I can load in a different program and have it do the same thing. In essence, that stored program computer is emulating or imitating a fixed program computer for each program that I load in. It gives me an infinite range of things that I'm going to be able to do. So what I want to now think about is, how do I take a description of a process in those mechanical steps and write it in such a way that I can load it into the computer and the computer can do the work for me. Before I do that, I need to think about what's inside the machine. So we're going to take just a second to open up the hood and look inside a typical computer. Basic machine architecture of a computer has some simple pieces. It's obviously got some memory, places in which I'm going to store things. Now up here in this memory, it could be data, but it also could be a sequence of instructions that are my program, that mechanical set of steps. I haven't said exactly what they look like, but you got a sense of them from what I did in that square root example. I'm also going to have a way to load things into the machine and print things out of the machine, input and output. We'll come back to those later on. Inside the heart of the machine, there are two elements. The first is often called an ALU, an arithmetic logic unit. And what this unit does is it takes information from memory, reads it in, often two pieces of information if I'm going to do an operation that takes two inputs, is going to do a primitive operation, could be addition, could be subtraction, could be testing to see if something is true or false, and then typically it's going to store stuff back up into memory. To make that happen, we need one more piece, and that's the control unit. And that's going to keep track of what specific operation I want to do in that ALU at each point in time. And inside the control unit, there's an important thing called a program counter. So very simply, when I load a program into the machine, in a second we'll get into how to do that, but I load a program into the machine. It's a sequence of instructions up here, and the program counter points to the location of the first instruction. And when I ask the machine to execute, that program counter reads that first instruction. It's going to cause an operation to take place, and it's then going to add one to the program counter, which is going to take it to the next instruction in the sequence, just as we saw in the square root example. That's going to do another operation, typically doing some arithmetic operation, moving things back into memory, and it's going to increase the program counter. Eventually, we're going to get to a test, and that test is going to say whether something is true or false. And based on that, we're going to change the program counter to go back up, for example, to the beginning of the code. But that's in essence what happens inside a modern machine. Control unit tells me where I am in a sequence of instructions. I've read into the machine, that stored program. That causes a simple loop inside the machine of operations. When I get to a test, it's going to potentially change the program counter. And when I get to something that says stop, it will, and it'll print something out on the machine. That's the heart of a machine. That's all there is inside a computer. All right, there's a lot of stuff inside there, but that's basically what the machine's going to do. And our goal is now to figure out, how do we write that sequence of instructions so that the computer can do the things I want it to? To summarize, a stored program computer then is going to be that sequence of instructions. It's going to be built out of simple arithmetic and logic instructions. It's going to be built out of simple tests, and it's going to allow us to move data around. And associated with that is going to be this special program called the interpreter that's going to execute each of those sequences of instructions in order, changing things with the flow of control when a test says, I want to go somewhere else. And then finally, when I'm done, print out the answer. That sounds great. So what are the basic primitives? Most machines will come, as I said, with simple arithmetic and logic operations. But in fact, you can go even simpler than that. And if you go back to that gentleman I mentioned earlier, Alan Turing, one of the greatest computer scientists in the history of the world, Turing showed that you can compute anything with just 6 primitives. In fact, there's something called a Turing machine, an example of which is shown in that little image on the slide. A Turing machine is an infinite tape with a set of squares on it. In that, each square there's a symbol, could just be a 0 or a 1. And what Turing showed is if you have 6 operations, and those are move left, move right, scan, read, write, do nothing, with just those 6 primitives, you can compute anything that's computable. You're now panicking and looking to find a different class, because if what you had to do was program a computer by saying move left, move right, read, write, scan, stop, you don't want to program. Fortunately, modern programming languages come with a more convenient set of primitives. But the fundamental idea is that with a simple set of primitives, you should be able to compute anything. Equally importantly, you don't want to just write everything in terms of addition, subtraction, logical tests. What you want to do is write descriptions, like that square root program that we talked about earlier, and then abstract them. And I'm going to highlight that word because abstract is going to be really important. You want to treat that square root as if the manufacturer had built a little primitive and installed it in your machine. You want to be able to use it as if it was something that came with the machine. And that's what the power of computational thinking is going to give us. One last thing about computation. Let's go back to that Turing machine idea. I said you could compute anything if you just had those 6 moves. There are some nuances to this. A more sophisticated computer scientist could debate some of those details. But there's a fundamental property which says anything that's computable in one programming language is in fact computable in any other programming language. Wow. That's amazing. It says, while you may get heated debates between people about whether Python or C or Fortran or Lisp is the best computer programming language, they're all the same. Okay, slight misstatement. Some are going to be easier. Let me rephrase that. In some languages, it's going to be easier to do some kinds of things than others. In MATLAB, it's easier to manipulate matrices. In C, it's easier to deal with web programming. But nonetheless, anything you can compute in one language, you can compute in any other language. And this is a property called Turing complete. That's one of the fundamentals of computer science.